Okay, so hopefully you survived the first video. As I mentioned just at the end there, we're going to use these probability distributions to talk about electron orbitals. Okay, let me go back and actually go back to the learning objective now. Okay, so the objective for this topic is for you to be able to represent the electron configuration of an element or ions of an element using the Aufbau principle. Okay? And so we're going to be hitting on electron orbitals, the Aufbau principle and orbital diagrams, and then I'm going to make a note about ground versus excited states in this video. And then there will be a third problem-solving video where I actually work out some problems using these orbital diagrams that will be uploaded a little bit later. Okay, so back to where we were. We had just got done talking about probability distributions and how you can use the mathematics of quantum mechanics to come up with the estimated or probabilistic region for where you might find electrons. So how does that help us, right? Like, what are we really doing? So probability distributions can be used to visualize spaces in which electrons might be in an atom. A common way of doing this is visualizing these spaces is creating three-dimensional shapes whose surface surrounds 90% of the total electron probability. That's what is depicted here in this bottom picture. Okay, and this is what you might have seen before when looking at different electron orbital shapes in the past. What this means is that based on the math and the probability distribution, 90% of the time we would find an electron inside of this enclosed space. Okay, these are simple orbitals, the 1s, 2s, and 3s. As you're going to see here in just a second, the different types of orbitals can vary in shape. But 90% of the time we would find the electron in that region. Okay, the specific shapes of these orbitals are not so important right now, and as I'm about to show you, they can get pretty complex, but they will become a little bit more important when we start discussing chemical bonding later on in the semester. So here you can see some of these other types of orbitals. I've got p orbitals here and d orbitals down here. The mathematical equations for these probability distributions can be run through computer simulations, and you can actually get these. It's kind of like it's kind of like data, right? It's a simulation that takes the equation, which you can't really read here, but that's okay. It takes the equation, runs it through a simulation, and it sort of shows us these different places where the electron might be, and so it gives you just a bit of a sort of a mathematical visualization of what the orbital looks like, and then you can take that, right, say where are 90% of these electrons, right, and you can draw these different orbital shapes. Okay, and like I said, the shapes in particular are not super important right at this moment, but they will become a bit more important as we talk about chemical bonding later in the semester. So let's really talk about what it is we are supposed to be accomplishing with this topic, right? Most of what we've done so far in my course is learn about something and then apply it to some problems, right? That's kind of what chemistry is all about, right? How do we take knowledge that we have and apply it to solve problems that we need to address? So what we're going to be doing is we're going to be writing electron configurations and drawing orbital diagrams, okay? And there's a simple concept called the Aufbau principle, which is actually super simple. It's the name sounds more complicated than the principle itself that we're going to use, okay? So assuming that all elements have the same types of orbitals, all right, so these types of orbitals that we get through the mathematical probability distributions. Assuming that all elements have the same types of orbitals, we can describe the position of the electrons in atoms by writing the electron configuration. of those electrons. Okay? And the Aufbau principle states that just as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the orbitals. Now, I am going to be assuming that you can either, number one, remember how to do basic electron configurations, or two, that you can go back and review and learn this on your own. Okay? What I'm talking about is the application of this thing right here. This is called the diagonal chart. This lists all the different types of orbitals that exist. Well, not all of the different types. Technically, there would be some more down here at the bottom. But for all of the elements that we know that exist, this covers everything, okay? I am not going to go into the nitty-gritty details of this. One of the reasons why I recommended certain people for AP Chemistry and not others is because, you know, retaining information that you've learned in the past is an important thing. And I only recommended people that I thought were capable of the type of retention that you need in a course like this, okay? Now, it's completely okay if you have forgotten how to do this process. It's not that hard. And I've got some links here to some videos and then also just some written tutorials on how to do this, all right? So I'm gonna whiz through this quickly. The standard notation electron configuration of an atom describes the location of all the electrons in an atom. This right here, this middle column, are some examples of standard notation electron configurations for these different elements. It tells us where the electrons are in an atom. Okay, so like the 1s is the name of the orbital, and the little exponent there tells us how many electrons are in that orbital. The noble gas notation electron configuration is an abbreviated version of the standard notation. It means the same thing, it just takes less space to write. Okay, and it's generally used for larger atoms that have lots of electrons. So as you can see here, for strontium, for example, we have a very long electron configuration, but when that is converted into the noble gas notation, it's much shorter. Okay, so these are sort of interchangeable, they mean the same thing. I need you to know how to do both of these things, okay? And so if you do not feel comfortable with that right now, then I need you to spend some time, maybe right now, reading over this, this website here, and then maybe watching this video tutorial on how to do this. Okay, so I'm going to assume that you know how to do the standard notation electron configurations. Okay, so for example, coming up with this right here, 1s1, 1s2, 1s2, 2s1, etc. What's going to be new for us, and actually some of you may be familiar with this aspect of it as well, is the orbital diagrams. Okay, I did not get into this in my class particularly, mainly because I don't think it's that important for just a first-year chemistry class, but it is important for AP. So an orbital diagram is just an alternative way of representing the electron configuration. Okay? Orbital diagrams have these boxes. Each box represents an orbital, and it's a little bit different than the written version in that you express a few different things. So, for example, each electron is represented by an arrow. The direction of the arrow represents the electron's spin. Okay, now this is not particularly important, at least I don't personally think it's particularly that important, knowing every little detail here, but basically electrons can have one of two spins, up or down. Okay, so in each of these boxes you're going to have an up arrow or a down arrow or both. Okay, the Pauli exclusion principle, as you can read right here, says that you can't have two electrons in the same orbital with the same spin. Okay, so you can't have two up arrows in the same box, you can't have two down arrows in the same box. If you're going to have two electrons in the same orbital or in the same box, they must have different spin. Okay, and the way that this works is as we build up through the elements, as each element gets one more proton, right? So hydrogen is atomic number 1, which means it has one proton. helium has 2, lithium has 3, so on and so forth, we're also going to be adding an electron. Okay, and once again, that's what the Aufbau principle says. Okay, so the name of this is more complicated than the concept. This just says that as protons go up, so do electrons. Okay, so here's how this works, right? The electron configuration for hydrogen is 1s1. So we're going to put one arrow in the 1s box, and that represents the 1 electron. Technically, this could be an up arrow or a down arrow. Okay, it doesn't really matter. Convention is to start with up arrows rather than down arrows. Okay? But you wouldn't technically be wrong by having a down arrow here, because you could just like flip the box upside down and then you have an up arrow, right? So now the electron configuration for the next element, helium, is 1s2. Okay, this means that we have 2 electrons in the 1s orbital. So we need to have 2 arrows in the first box, and they have to be different spin, right? So up arrow, down arrow. That's it. I mean, that really is the concept here, guys. There's a few little things I'm going to get to as I go through the rest of these examples, but that's basically what's going on. We're just taking the written version of the electron configuration, which you should know how to do already, and we're just representing it in a different way in these orbital diagrams. Okay? So you can see here, as we go to lithium, we just have another box, the 2s orbital, with an arrow for the 1 electron. Beryllium has 2 electrons in the 2s orbital, so we have an up and a down. And then we get to boron. Okay? Now, the p orbitals are a little different. Okay? The 1s orbital, all right, and this is some stuff that you ought to recognize, the s orbitals can only contain 2 electrons each. Okay? The p orbitals can contain 6. All right? And that is because if we look here at these shapes of the orbitals, there are 3 different orientations that the p orbitals can adopt. There can be a p orbital in the I know this is really hard to read, but there can be a p orbital in the x orientation, y orientation, and z orientation. Think of it as like 3D, right? There can be an orbital that points like this way, and then this way, right? Like the 3 dimensions of space. Each of those shapes, each of those orbitals can hold like 2 electrons. In fact, the plus and minus signs here represent like the positive and negative spin, or the up and down spin of those 2 different electrons. Long story short, p orbitals can hold 6 electrons, but when we do this in the orbital diagram, okay, we have 3 different boxes there, okay, and those so each box can only hold 2. So if you know that you're working with a p orbital, you should draw, when you're doing an orbital diagram, you should draw 3 different boxes, right? Because the p orbital can have 6 electrons, and if each box can only hold 2, that means you need 3 boxes, right? For 2 plus 2 plus 2 equals 6. Now, the way that these arrows get filled in for the electrons in the p orbital is you need to do this in a particular way, okay? So it doesn't really matter which box you start in, but once again, the convention is to start in the first box, okay? So for boron, with its 5 electrons, we have 1, 2, 3, 4, and then that 5th one goes in that first box, once again in the up direction first, by convention. Now, let's move on to carbon, okay? So carbon is atomic number 6, 6 electrons. Our 1s and 2s orbitals look the same as they did before. We're going to have that 1 electron in the 2p orbital in the first box. Now the question is, where does that second electron in the 2p orbital go? Where does that second electron go? You sort of have two real options, right? You could put it in the second box, or you could put it in the first box with an opposite spin, right? So the rule is, and this is, I love electron configurations because there really are just like rules that you can follow, right? The rule is that it goes into a different box, okay? And that's going to be true for the 3rd electron in the p orbital as well, right? So as we move down to nitrogen, we're going to spread all 3 of those electrons in the p orbital into those 3 different places, okay? And the explanation for this is because electrons are all negatively charged. Okay, so all of the electrons are negatively charged, which means they're all sort of repelling away from each other. So if they have the ability to, they're going to occupy different physical spaces rather than all being bunched up together. Okay, so that's why they spread out in these three different like suborbitals of the p orbital overall. Okay, and one other thing I do want to note here is that notice how all the arrows are in the same direction. Once again, that is not only by convention, but that is actually also an additional sort of aspect of this. All of the electrons in the p orbitals need to have parallel spins, meaning like the same direction. So you wouldn't do up, up, down, or up, down, up. Whatever you start with, go ahead and finish that out, right? Up, up, and up. Okay, and then the next three electrons are going to be very simple, right? We've filled in one for each of these p boxes, and so then we're just going to do the down arrow, down arrow, down arrow for the remainder. Okay, that's basically it when it comes to orbital diagrams. Okay, now obviously it's going to take some time to sort of get used to working with them, but that's essentially what's going on here, right? It's just filling up the boxes according to those rules. Okay, so I also want to take a moment to talk about the shape of the periodic table. Once again, I did talk about this in my class last year, and so you also likely have heard mention of this. Depending on the final term in each element's electron configuration, let's say we wrote the final term in each electron configuration in the box for that element. Okay, so if you see here, like for hydrogen, there's only one term, 1s1. Same for helium, 1s2. For lithium, right, lithium's electron configuration is 1s2, 2s1. So if I take that final term, right, the 2s1, and I write that here, okay, and then I just do that for every other element, right, what you end up seeing is that the the periodic table is arranged according to the final term in that element's electron configuration. Okay, and so here we have the entire periodic table written out, and what this shows us is that these left two columns, with helium being the exception here, all of these elements, their final electron is in an s orbital. Okay, same thing here. All of these elements, their final electron is in the p orbital, or is in a p orbital. Same with the d orbitals here and the f orbitals here. What this does is it sort of creates some sections of the periodic table, and I just wanted to mention this because it may come up in the textbook or in some other resources that you might read. These different regions are referred to as like the S block, the P block, the D block, or the F block. Okay, so like this would be the S block, P block, D block, and F block. Okay, and I wanted to make one last note here before I finish this this video up about ground states versus excited states. So by default, it is assumed that electrons in an atom are at their ground state. Okay, ground state electrons are normal, how we would tend to think of them by default. Right here it says all electron configurations are written with this assumption in mind. So take this number 1 right here, for example, 1s2, 2s2, 2p6, 3s2. If we add up those numbers there, that's 12 electrons. This right here is the ground state electron configuration for magnesium. 12 electrons, atomic number 12 would be magnesium. Same thing here. Okay, this is an orbital diagram, but this is 1, 2, 3, 4, 5, 6 electrons. That would correspond to C for carbon. This right here would be the ground state electron configuration for carbon. However, just like we saw at the very beginning of this video series, electrons can absorb energy. okay? And when they do so, they actually become excited, okay? When they absorb energy, something happens to their configuration, right? They're no longer in the spot that they were before, okay? We started to see this a little bit when we talked about Bohr and the Bohr model. Now that we're actually starting to write and draw these electron configurations, we can really express what's going on here. So this is just an example, right? You've got the carbon ground state, you add some energy, and what could happen is an electron that is located in a lower energy level, say this, or a lower energy orbital, say this 2s orbital, that electron could actually jump to an excited state, right, into the p orbital, in which case we would represent that in this way, okay? This right here represents an excited state of carbon. This would not be how carbon would be normally. Something would have to cause the electron to jump. Something would have to cause this atom to adopt this electron configuration. That would be the presence of some excess energy which the electron absorbed. Okay. Let's take just a minute here to look at this question. It says, which electron configuration represents an atom in the excited state? So take a look at this. See if you can look at those different electron configurations and spot which one might be the excited state. The correct answer here is number 4. The reason is, if you take a look at the electron configuration, we have 1s2, 2s2, 2p5, and then 3s2. Normally what we would expect for a ground state element is that the p orbital would fill up before electrons would be placed into the s orbital. So we would expect this to be 1s2, 2s2, 2p6, 3s1. So what's happened here is that this element, this atom, has absorbed some energy. One particular electron absorbed that energy, and it moved from its ground state of being in the 2p orbital to being in its excited state at the 3s orbital. Okay, well, that's it for the notes portion of this topic. I do really apologize for the length and sort of breadth of knowledge that we're encountering here. In the future, I may end up breaking this up into 2 different lessons or trying to tackle this in sort of a different way, but it is what it is. So you guys are capable. I believe you'll be just fine. There's going to be a third video on problem solving where I'm going to do some drawing of these orbital diagrams and also some interpretation of what these electron orbital diagrams can mean. So thanks for watching, and I'll see you next time.